Hello everybody and welcome to my channel. In the previous video where I took a first look at the Swift concurrency story with async, await and a little bit of structured concurrency, I said back then that the concurrency story in Swift it's coming and it's coming huge. It has many things all interrelated to each other, so it's a little bit complex to get the full picture, but today we're gonna focus in one of those parts. Today we're gonna talk about actors, so make sure you watch first the previous video so you at least know a little bit more what's coming. So the first thing to notice is that the actor system, it's kind of like a different thing than what we saw the other day with async await and structured concurrency and all that stuff. They are different concepts. You can use one without using actors, and it's basically like actors are built on top of the async await story in Swift. So don't think that the only things that are coming to Swift are actors and then you're going to be forced to use actors and all that stuff. That's not what's going to happen. But instead, the actors are built onto the primitives that are async await. We're going to talk about actors. The actor model is a computational model, and as such, it has many things related to theory. Okay, there is a lot of theory behind it. There are plenty of other videos where most of them talk about practical implementations, specific implementations like ACA and other ones. But there is one specifically that I'm going to link onto the description that talks about the theory behind it. It's from people that knows back then the history and all that stuff, and it's super interesting. So I recommend you to watch that if you are more interested in knowing the theory behind actors. I haven't worked with actors personally, so they take all of these with a grain of salt. I know what they are, I know how they work, I've been trying a bunch of things, so I think I have a good understanding, enough understanding to give you the initial tools, because that's what I want to give you. I want to give you the initial tools, the understanding, so if you're interested in it and you want to be ready for when this comes to Swift, you can go and do your own exploration. But I want to give you like a first taste, the first tools for you to understand what's going on, what are actors, and how they're going to impact my day-to-day. So let's get started with a little bit of theory. I won't go too deep in the theory of actors, but at least I want to explain you some of the basics of this theory and the rules behind them and all that stuff, so you understand better the reason of the things that we're going to show you later in Swift, and also how Swift has adopted this system, why it's important for Swift in the long term in terms of concurrency, and what's kind of like the places where Swift has diverged a little bit into the more classical aspect of it. Actors come from the actor model, which is a computational system, and as any system, it basically needs a bunch of actors, because one actor in its own, it doesn't do very much, so you need a bunch of them. Now, what is an actor? You can think of an actor as an entity that you are gonna hear this word in many videos and descriptions that has a mailbox. I honestly recommend you that you ignore the mailbox part, at least for this video. You can go later and read more about it and watch some other videos where in other implementations, I think, and especially in the theory, the mailbox is more important. But I honestly think that on Swift, it's not something you're gonna encounter on your day-to-day. So I would say don't worry too much about it. So you have the entity, the mailbox, and then you have an address. So this is kind of what is an actor, these three pieces all together. Now, what defines an actor? Well, an actor is something that can do some processing, it can store some data, and it can communicate. These are the three things that describe an actor. Now, the storage part is very important because it's kind of like what distinguishes an actor system from other systems like object-oriented programming, where you have something similar, we call them objects, and these objects have some data here, but that data doesn't have anything special about it. So the important thing about an actor is that the data of the actor, we say that is isolated into that actor. Nothing from outside the actor can see or touch that data. The only one that can do anything with that data, it's the actor itself. That's kind of the things that distinguishes actor from other systems, and that helps a lot in getting rid of bad things like data races and all the stuff that we are worried when we're talking about concurrency. So what an actor can do? Well, the first thing an actor can do is create other actors, because you need a system to get the concurrency and all the benefits from the actors. One actor doesn't do much, you need a system of them. So an actor can create other actors. You can imagine that this actor can create as many actors as it needs. Now, once these actors are created, you need a way to communicate. So an actor can send messages to these other actors. Nothing weird for now. But the important thing you need to understand is that this is sending a message. It's not making a function call or anything like that. It's not accessing directly that actor. It's sending a message to that actor. It reminds me back to Objective-C when we said that Objective-C sends messages. You don't call functions like in the C sense. You don't call a C function in Objective-C. You send a message to an object and that object reacts to that message. It can react just by executing what you are telling him, like usually, but if you hook into all the runtime power of Objective-C, you can do things like proxies and stuff like that, and that's all because you're sending messages around. You are not actually calling functions. It's a very similar concept here, where you are just sending messages to other actors. You're not having calls directly to them. And that's very important because you don't have a direct access to the actor. So as we have drawn here, an actor is all these things together. What you do is you send messages to the inbox of the actor. You send messages to the actor. And how do you have a grasp of the actor? Well, in reality, you don't have a grasp of the actor in the sense of I don't have something that it's pointing to that address in memory or to that object itself. What you have is what we call an address. You have the address of the actor. But that address becomes a many-to-many relationship. You can see that you have like this circle here. That it represents the entity of the actor. Gives you the identity. But from the outside, you have no clue what's the identity of this actor. You only have the address. So what you're sending here is actually messages to these addresses. And there may be actors that have one address, but many actors behind it. So one address can point to many actors. Imagine that you have a system where you want to proxy or load balance the load of execution. You can send all the messages to one single address, and the actor system in reality behind it, you will have different actors. That's possible. But you also have the other way around. You can have a system where one actor has multiple addresses, and it gives that address to different subsystem or external systems, and each of these external systems, it's thinking that it's talking to a different actor, to a different address, but in reality behind the scenes is always the same one. So you can see that this address gives a lot of power. This power is very important in something like distributed actors that we're going to talk in a bit. But for now, just think that you have actors sending messages to the addresses of other actors, not the actors. And of course, the last thing that an actor can do is take a message from the mailbox and execute whatever it needs to do. In the theory, they talk about that an actor decides what to do for the next time it reads a message, but I find that very confusing in practical terms because it seems like it's saying, I don't touch the wall now, but by the time that I receive a next message, the wall will be updated, which may be very nice in theory, but in practice, I mean, we're just mutating our local state, so I don't think we should worry too much about it. Now, as you can see, this system, it's easy to scale, and you can make it very fault tolerant, which is what a lot of these real life implementations that have been in the wild in things like Akka and stuff like that, they focus a lot on distributed systems. Why is that? Because the fact that you have the difference between an address and the entity behind it, it makes it very easy to create something like a supervisor. Imagine that you have an actor that is supervising these three actors. And imagine that this one fails, for example. Well, this supervisor can actually kill the actor, destroy it completely, and recreate a new one. And when it recreates a new one, the address is still the same. You're just creating a new entity that is behind that address. So for the entire system, it's like nothing never fails. And if something is corrupted and fails, you just destroy it, create another one, but nothing else changes. And that's super important for network distributed actors, which is, I think, the main focus of many of the other implementations. Let's forget for now distributed actors because Swift, they're talking about it for the future, but not right now. So let's focus on how this is going to impact us in our day-to-day in Swift. So first of all, if you want to try this yourself, this is the proposal that introduces actors in Swift. Of course, related to all the other web of proposals around concurrency, but this is the main one that talks about actors. So first of all, let's take a look at what we will be doing right now, even including all the async features, but without actors, and what problems will that give us. So to see these issues, let's see the classical example of a bank account. This is the classical example that you get when you want to explain concurrency and data races and all that kind of stuff. So let's take a look. So we just have a class bank account with an immutable property for the account number, which is just an integer. And we have a balance, which is a mutable property because of course you want to change the balance of a bank account, which is a double. And this is just the initialization for this class. Now let's imagine that what we want is to move money from one account to another, but we are in a concurrent system and we want to do that with multiple accounts. So if we defined one error in case like there are insufficient funds, we can throw that error. And now we're gonna start coding our system. So let's start with defining 3 bank accounts. All of them like have consecutive numbers. The numbers don't really matter, but now we just have 100 of money into one account and the others are 0. So let's try to move this money into the other accounts. And for that, let's just define a transfer function in the bank account that given an amount of money, it's transferred into another account that it's also given. This function, of course, is asynchronous because we are playing with a concurrency system. And we want this function to support throwing because, of course, if there is not enough money, you need to throw an error. Then after checking that there is enough money, we remove the amount from the current account from self and we deposit this money into the other account. As you can see, there is nothing weird going on here besides having an async function, but there is nothing weird that we could not do in Swift right now. Now, before we continue, let's make the bank account conform to custom string convertible so we can see the information of the account on the console easily. So now that we have the 3 bank accounts and this transfer function, we can start calling into the account 1 to transfer 90 amounts of money into the account 2 and the same to the account 3. And then we can print what the current state of the bank accounts is. But first, let's move this into a new function to make it easier to play with, because otherwise it's going to have errors because I'm throwing into the main context of the application and it's going to start complaining all the time. So if we run this now, we see how immediately we get the error of insufficient funds because this one succeeds properly, but as soon as we get into this second one, there is not enough funds and it throws and then we show the error. Okay, but we want to have a concurrent system. Now, I'm just making it fake here, so it's not a super good scenario, but I want to put some code here so you can see what will happen in a more concurrent system. So I'm going to replace these 2 calls with an async detached, and all of this is still in flux, so don't pay too much attention on here. Just think that this is basically starting the work of the transfers in a detached context and it's running concurrently between each other. And because this is kind of giving me a handle for the underlying task, I need to wait for both of them to finish basically. And you can ignore all this code. I just have to put it here to basically have a more realistic state to show you the problems that we will have in reality. And as you can see, nothing has changed, but to prove you that it's not going to be always correct, that there is data races here, let me just, instead of doing this, let me kind of massage a bit the code. And here I'm just starting an infinite loop, which is not going to stop until we actually see a data race, basically until this code finishes instead of throwing an error, because throwing an error is what we actually want to happen. So if you run this, you see that during many iterations it was fine, but then finally we got the data race. What happened is that in the concurrent context, this check happened, but then somebody else changed the balance and now another context changed the balance at the same time. So typical data race. Now, how do actors help us with this? So in Swift, an actor is a reference type, most like a class, but that you start defining it as an actor. Instead of a class, you define it as an actor. And now you are not working with classes anymore, you're working with actors. And the nice thing of that is that now we have a system that it's integrated with the language, and that allows the compiler to understand and enforce all the rules that we discuss about the actors. In the same way that the compiler enforces that the types of our variables make sense. So it's like now the compiler has superpowers and is able to understand parts of the concurrency and help us a lot on avoiding data races. So now that we have an actor, this actor is making sure of protecting its state. The let property, there is not much to protect because it's immutable, so it doesn't really matter. But the balance, which is the variable that is changing, that must be protected. And now that this is an actor, this property is fully protected. If you're still confused about what this does, you can think of it as an actor being a class that has an internal queue, like a dispatch queue, and that magically it makes every function that you call on that class run inside that queue. So you are sure that there is only one piece of code, and it's basically a locking mechanism. There is only one piece of code that is running inside that class. That's basically abstractly, like as a comparison, what an actor is and what it does. So now we have an actor. Look at this, how beautiful it is. We have compile time checks that we are doing something very bad. What we are doing is we're accessing isolated state from another actor. What is isolated state? We differentiate the state of an actor between isolated and non-isolated. Isolated state, it's basically this variable. This variable, it's dangerous to be mutated from the outside and even to be accessed from the outside. So that's isolated state. It means you cannot do anything with this variable unless you are in the isolated context of the actor. What's the isolated context of the actor? Well, if you are running inside a method inside the actor. As you can see, it allows me to change self-balance because I'm on the context of this actor, but I cannot change the other balance because I'm not on that context. I'm on my context, not the other one. And that's a huge difference. And here you see the compiler telling you the actor isolated property balance can only be mutated on self. And it's the same thing for accessing the read. So how can you change this? Like imagine that you want to print the other balance. That's going to be the same, but it's instead of a mutation, it's going to tell us you cannot read from another actor isolated context. So to do that, it's very nice because you just need to mark this as an await. So if you do an await, what this is saying is like, yes, I know this is not my actor's isolated data, it's from somebody else. So let's do an asynchronous call to that. And when that actor gives me the data, that's fine. I don't want to do it immediately. I can wait for that actor to be ready, to be all consistent, and then it's going to give me the data just to me, and it's going to keep the consistency. So that's what it's doing. It's very important because you see that we are not marking this as an async. See, this is an async function, but this is not. So how? So it's because the compiler understands the difference between one actor's context and the other actor's context. And if you want to cross from one to the other, you always need to do an async call because, as we mentioned before, actors just send messages between them, and those messages are asynchronous. Now, a very important difference that I found from the theoretical system of actors is that on the theoretical system, you send a message to another actor and you are not waiting for a response. Like now, that makes sense because if you think about distributed systems, you just want to send messages and don't have to wait because that will be more blocking than it should. In Swift, though, I think they have been more pragmatic about that, and even if maybe behind the scenes, the way this works is sending a message to another actor, telling it the address of the actor to get the response, and then sending another message with the response, from our practical usage, when we are writing code, all of that doesn't matter. All of that doesn't matter. The only thing you are doing is just writing normal code with an await, and that automatically does a hop into the other context of the actor, and it comes back into yours. And it makes sure that it's consistent, it's thread safe, and all that stuff. It's pretty cool. So here, instead of writing this like this, we need to make sure that it runs in the context of the other actor. To make it nice, we can just separate this logic into another function that we just call deposit. You deposit some amount of money, you check that it's not negative, basically, and then you just mutate the balance. As you can see here, we are on self, so we're just mutating our own balance, so we are on this isolated context, and it's perfectly fine. Most importantly, see how this function is not async, because we are not touching and calling any other async function, so it's completely an async function. And now with this, we can call deposit on this other actor with the amount. And still, you see the compiler that is telling me, well, the expression is async, and you're not using an await. But it's not really async. The whole integration with the concurrent system is very nice because this function is not async, it's a synchronous function. I'm just touching my own state. But still, because the compiler knows that this is another actor and that you are crossing the boundaries of your actor to go into another one, it's telling you the same thing that it was telling us here. No, you need to write the await because you are going to have to wait for that actor to be ready to answer your message. And now this compiles. And as I was saying, even if this thing doesn't return anything, this await, it's gonna wait for the deposit to finish, and then the execution is gonna continue. That's because all this actor system is built on top of async await and the Swift Structured Concurrency. which structured concurrency is a topic that I want to talk about a bit more in another video, but basically that rules enforces that you finish everything before your context ends. So this await is actually have to await for this to finish, which in this case is fine because it's synchronous, but you could imagine that there was more async calls here, and still this will mark a suspension point here and you will have to wait. And of course, just to say that there are ways of doing this without waiting, like kind of similar to what I'm doing here. I'm just doing an async detach or an async call, and it's like saying I don't want to wait, but we should try to avoid that because it breaks the structured concurrency, but that's another topic. So we still have this error here, and this error, it's kind of important. It shows us kind of like what's the reality of this. It's not going to be as straightforward as just taking all the classes and making them actors. That doesn't make sense. We need to think about the systems that we want to define. For example, there are protocols that are sync because there is an alternative right now. All these protocols that are sync, like this one, you cannot make your actor conform to this protocol because look at the error that it's giving us. This debug description cannot be used to certify a protocol requirement. That's because by default, this code here, it's isolated on the actor's context. But this protocol, this debug description, it's just a synchronous function, so it cannot wait for the actor to be ready to jump into that context and do all that stuff. So what it's telling us is use this non-isolated, which is kind of the opposite of isolated, which is the default for this thing. So by default, you can think of its actor isolated, and then you are saying, no, make it non-isolated. Instead, this let, by default, you can think of it as like it's non-isolated because it doesn't matter. You can touch it from the outside. Because you can only read it and it doesn't matter. And the balance is isolated. So you could actually mark this as non-isolated too. And then all these protections are out of the way. So yeah, don't do that. But here now, if we do this, we are back again at the problem. This balance cannot be read because we are now outside of the isolation of our actor. So you can see that you are, well, in one way I need to mark it non-isolated, but I cannot do it because I want to read this. So basically this cannot be implemented in this way. So let's comment this for now and just write a function that tells the actor to print itself. So we're getting the same thing, the same output, but because we want to be reading from the isolated state of the actor, we need to tell the actor instead, print yourself. Don't give me any information, just print yourself. And if we run this now, you can see how it's going, you see, but there is no data race. We could keep this running forever, but in theory there shouldn't be any data race because we are making things properly thanks to actors. So this is the huge benefit that it gives you, that the compiler is checking for you that you don't access state that you shouldn't be able to access and modify it from the incorrect isolation context of an actor. So that is very good and it's amazing. But I don't want to leave this video without telling you about one thing that you need to be worried about. So in the theory of actors, they say that actors basically read one message at a time. That basically means that if you get a message to run this function to transfer from this account into this one, you are going to get one message at a time and run it, and take another message at a time and run it, and so on and so forth. I don't think this is exactly how the Swift implementation is done, because Swift has opted to implement the actor system, the functions on the actors, reentrant by default. There are conversations of having options to enable non-reentrancy, but by default it seems that we are going to have reentrant functions by default. What does that mean? This function, so an actor isolated function, which is what this is, when it suspends, it creates a reentrancy point. That means that, for example, if we had something here, like this, let's say task sleep or 1 nanosecond, you will see that because this is an asynchronous thing, we need to mark it as an await. Remember from the previous video that an await marks a suspension point. So what reentrancy means is that even if you are on a function that is actor isolated, a suspension point marks also a point of reentrancy. It means that usually if there were other messages coming into this mailbox, so if other messages were trying to execute this, a non-reentrant system will wait for this one to finish and then the next one. and then it will run it again, and then the next one, and so on and so forth. In a function that is reentrant, it means that this suspension point says that nobody can run this multiple times, but as soon as you are here, it means that this is free again. And somebody else can go and run one at a time, but it can run this. And when it's here, another can go. So if everybody's waiting here, it means that this is unlocked. So this piece of code, everybody can run, and that's very dangerous. I think we need to be very, very, very aware of this, because if this is as default, then it has many, many good things. Like, for example, let's talk about what will happen if we don't have this. Well, it means that if there is no reentrancy, and imagine that you wait on the other deposit to do the amount, and the other deposit waits on the one you are sending. So if two actors are waiting on themselves, that's a deadlock, and you are screwed. Like, that's very hard to reason about and to find and debug, and so like we are kind of messed up. With these systems, we reduce these deadlocks of one waiting for the other. Then we also get better performance, because if you are waiting here, why nobody else can go and execute the part at the top? You know, it's like we are doing job in advance. There is no unnecessary waiting, and there is better scheduling at runtime and stuff like that. So there are very good benefits, and I understand why the Swift core team has decided to go in this direction. But there is also a big dangerous thing, which is now your state, it's not consistent if there is a waiting point. And you can see immediately how if I do this and I run, then we're going to have data races very soon. Because this suspension point, which means that like the actors are all waiting here, but the check has happened. So as soon as one crosses, it's modifying the balance, but the other didn't check the balance because the balance was checked before the state change. So you can see how easy it is to create, again, data races. So we need to be very careful. The idea is that you should make sure that your state is consistent across suspension points. So basically, don't do an await between the place where you check for your state and the place where you do something with your state. That's basically what you need to be careful about. I don't want to discourage anybody from using actors, but we need to be thinking about it, because I'm afraid that if we don't say it from the start, we're going to be shipping a lot of issues, and I'm not happy with that. I know what you're thinking. This is very nice, but I'm not going to implement a bank account system in Swift. I'm just going to make UI applications, and how does that help? So I'm very happy to tell you that it will help tremendously. There is another special context that is called global actors. So this allows the developer or libraries to define actors as global actors, where you can mark pieces of state on your application or function on your application with a special annotation that says, okay, this function, even if it's not defined inside an actor, so like we have here, we're defining functions inside an actor. Even if we don't define it inside an actor, we can make that function run in an actor's context. So for example, if we did a function to touch UI view, for example, and we all know that that needs to happen on the main thread, we could annotate this function to say main actor. And now when we call this function, automatically from any context, from any actor, from any thread queue, whatever you want to call it, it automatically will do a jump into the main actor. So that's a super easy way to ensure that your code runs on the main actor. And that's amazing, because now you can imagine how Apple can make the entirety of UIKit an actor, which is running on the main actor. And then anytime you want to touch something on UIKit, if you're not already on the main actor, you're going to have to jump into it. And that's amazing, because we have compile time guarantees that we're not messing UIKit from a different thread, which causes a lot of issues. Nowadays we have that runtime check on Xcode, but still, that's a compile time guarantee that we are not messing up with the state outside of the main thread. And because all of this works on closures, you can imagine that this is defined on your view controller, for example, and you get a call from a button that it's save results. Well, this is running on the main actor, so that's fine. So this is making the start saving a spinner, the loading a spinner, automatically run on the main thread, which that's good, because that's what we are touching a view, so that's good. But then we, with this syntax, don't pay too much attention on this part of the syntax, but we are basically going into the background, and we're starting a task to do something on the background, okay? But we're marking the closure itself. We're marking the closure as main actor. Inside this closure, we're actually running in the context of the main actor. But look at this. The first thing we do is we jump into a background context to do a save. So we await on the background actor to do a save. So that will automatically jump into the background actor, do all the work there without blocking the main thread, everything nice, everything at 60 FPS, pretty cool. And then when this finishes, automatically you are back on the main actor. You don't have to dispatch async into the main queue. You don't have to do any of that. This is amazing. All the actors is super cool, but I think the thing that's gonna have the most impact is gonna be this, like for sure. So that's it for today. That's everything I wanted to tell you, like an introduction to actors, a little bit of theory, and a little bit of showing how in practice it in Swift and how these things differ and what's gonna be the impact of it on your day-to-day. I know these videos are a little bit long, but I hope that you all learned something about it. If you have any questions, just drop them down below in the comments, or you can follow me on Twitter at alexito4. I'm not an expert on this, but if we're learning all together, I think it's gonna be much fun. Now that you know what an actor is, and remember, it's kind of a class with a queue, like look at your code, because I'm telling you that you already have something like an actor somewhere. For example, I was looking at my code base the other day, and I actually saw a database manager from 7 years ago that it's still working and it's perfectly fine, and it's actually a class that doesn't expose anything and just has methods that all of them run with a locking mechanism in a dispatch queue. So that's like an actor. So for us, it will be very easy to just migrate that into an actor because it's what it is already. It's just that the compiler doesn't know. So now we can tell the compiler is going to check everything for us. And well, it's one important part of the Swift concurrency. There is a lot of parts, but it's one very important part. And I'm sure in the future, Swift and Swift code, it's going to be way safer, way easier to work with concurrency thanks to all of this that we are just seeing today. I think the next video it's going to be about the structured concurrency. I've talked about it, I mentioned it a little bit, but I think it's something that I want to tell you why it's important and why Swift is going so rigid into it. So hopefully very soon we're going to have a video about that. Thank you for watching and see you next time.